Okay, we're almost here. Okay, it's a bit of work in this, isn't it? So we've now got to do the odd solution. So now we get A1, just check I've got the right notation here, A1 e to the minus k plus kx, x is less than zeta, we get sine the B1, kappa zeta, okay, remember this is a kappa, the x is between, the kappa has the same formula for even or odd, and then we get minus A1 e to the kx, e to the minus for x is greater than zeta. So this is the odd solution. Okay, and we match w and its derivative at, we can either do it plus or minus zeta. Once it matches at one, it'll match at the other. Okay, so we're going to get A1 e to the minus k zeta is equal to B1, and it's minus because we're matching at minus zeta. Oops, I should have a minus here, shouldn't I? B1 sine kappa zeta, and then match the derivatives as well. So that's going to be A1 here, k A1 e to the minus k. So I'm matching here at minus zeta, just to be clear. Derivative of sine is cos, and it's going to be B1 cos with a kappa zeta. So if I write that in my matrix as before, A1 B1 equals 0, it's almost identical to what we had before. We can get rid of the exponentials. Sorry, whoops. I can't do that yet. Minus kappa zeta sine, so minus k zeta sine kappa zeta, and k e to the minus k zeta and cos kappa zeta. Okay, and obviously I bring this over, sorry, I've got to put a minus sign here. Alright, so we want the determinant of that to be equal to 0. Okay, so we're going to multiply them out, and we can divide them, and then we can divide the kappa zeta. Clear this. We want the determinant of sine kappa zeta, k e to the minus kappa zeta, kappa cos kappa zeta to be equal to 0. So we get e to the minus kappa zeta, kappa to the minus cos kappa zeta is minus k to the minus kappa zeta sine, minus k zeta sine kappa zeta equals 0. And then we get rid of that, divide it out. We're going to write it in terms of tans again. Let's check that's what I've done. Yep. So we get very similar equation, tan almost identical, is equal to, and I take it over to the other side, I'm going to get minus kappa over k. Okay, so exactly as before, we can solve this equation here, right? And draw a little picture of it and work out what the solutions are. So I'm going to do that here. So let's just go through it. Here's tan, dot, 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 dot. We'll assume again that z is equal to 1 for simplicity. Just have a look at the solution. Doesn't make a lot of difference, it just scales it if you assume it's not. Okay, as always, we can write this as equal to minus k minus kappa over the square root of b squared minus b minus kappa squared. Okay, so what does that equation look like? So let's draw a picture of it. So what happens to this curve here? This is my kappa. So somewhere down here we have square root of b. And at that point there, when k goes to the square root of b, this is always negative, right? If k goes to the square root of b, it's an asymptote. You could have turned it around and written cotangent and shifted everything and got this similar expression, but it doesn't really matter, does it? And when kappa is equal to 0, this thing's negative down here at 0. And that doesn't count. We're not interested in the solution when k is equal to 0. Okay, lambda has to be lambda is equal to 0. It's a degenerate case. It's not a solution to our equation. So it comes down and it goes asymptotically down like that, and it'll have two solutions. And you can see here what I was saying about the odd solutions mightn't exist because of that. If this is the square root of beta here, then it's going to go asymptotically down and we'll get no solution. So we get a finite number, possibly none, for the odd solutions. And you can start to see here where they appear. The other ones came down like this. So this will be, so if you looked at the other solution, if I drew it on the same curve, the one we had for the even, this is the even curve, then you can see here, first solution, second solution, third solution, fourth solution, fifth solution. There'll be 5 solutions to these equations. 1, 2, 3 will be even and 2 will be odd, and they'll alternate. Coming down to this magic point here. They don't continue after that.